You remember? Surface integrals? Parametrizing surfaces and surface integrals. So today we're in the last type of integral, and then after we talk about this stuff today, maybe by the end of class, we could take a look at the different types of integrals and try to make comparisons, finding similarities and differences.
There's something about a second vector operator that's talked about last time. What we're talking about.
The grad, div, and curl are the only ones that we really talked about. I don't know. Let's make a list of integrals that we know. Actually, let's not make the whole list. Let's just talk about the path integral. And remember, the path integral takes a scalar function, and we use R, right? And integrates over a curve with respect to the arc length. And then in doing so, we need to parameterize C and then we get to rewrite this abstract integral into something that we can actually integrate. And it becomes a single integral, which should be manageable for us to do. So remember that the path integral is over a curve, and it takes a scalar function. And then we move to a line integral, which is still over a curve, and we need to parameterize. Except this time we're going to integrate not a scalar function but a vector field. And so because it's a vector field that goes in there, we can't parameterize by arc length anymore, or we can't integrate over the arc length anymore. We have to integrate over the tangent vector as we're going along that curve. And so to express that, we use the dr with an arrow on top. And one way to get a working integral out of this that we can actually compute is to take your vector field and actually dot it with, well, you can't dot it with the magnitude of a derivative because the magnitude is a scalar. So you actually take the derivative itself. And then after you take the dot product there, you'll get a scalar function that you can just single integrate over the interval a to b. Now last time, we took the surface integral, which is kind of like the path integral, because what you're going to do is you're going to integrate over a surface. Now, to integrate over the surface, you need to parameterize the surface with some parametrization with two variables this time, because it's a two-dimensional object. The surface is in 3D, but it's a two-dimensional object in 3D. And then we integrate this, or we parameterize this, and when we parameterize this, we have values for u and v. Now, if they turn out to be constants, that's great, but sometimes they won't be constants, so we're going to have u and v as an element in some domain in 2 dimensions on the UV plane. So that could be done in the XY plane, that could be done on the R theta plane, that could be done on the phi theta, or whatever the variables might be. But the point is that this is a 2-dimensional object. This time we're going to take the surface and look at it flat on some 2-dimensional plane. And so that's what's going to happen to our surface. We're going to integrate a scalar function over the surface. And our notation for that is capital S, d of capital S. Now that turns out to be the arc length, or not the arc length, but the surface area element. We're integrating over surface area, is sometimes what we say. And so this becomes a working integral for us, where it's a double integral over the flat 2-dimensional D instead of the 3-dimensional surface that's wavy or whatever. And then we basically do what we did last time. We're going to put the R of uv into the function. And so now our function, which used to be x, y, z, is now going to become u's and v's. And then this is the surface area element is the magnitude of that perpendicular vector that's perpendicular to the 2 tangent vectors on that surface for each of these little cuts that we take. And then last time I put du dv, but this time I'll put dA because that's our general idea for d something, whether that would be x and y, which is what we're used to, or in this case u's and v's. You know it's some area element in 2 dimensions. All right, so that's our setup. And the next logical step from a path integral to a line integral, and then you're going to take a surface integral, maybe to integrate over a surface, but instead of putting in a scalar function, we will put in a vector field. And so that's what this last type of integral will be. So this is the flux integral. They call it a surface integral also, just like they call the path integral and the line integral a line integral in the book. They call the surface integral and the flux integral a surface integral. Now, I still want to make the distinction, but there's really another nice way to put it together when we see it. We see a couple of versions of this flux integral. And the flux integral, if you look at the pattern that we went from a path integral to a line integral, and then so we just extend the surface integral, where instead of little f, a scalar function, we're going to take a vector field capital F. And so then the differential form, or the differential that comes in here, has to be a vector to deal with the vector field. So this is a capital S with an arrow on top. Yeah. A surface integral takes in a scalar function, and the flux integral takes in a vector field. So a working definition would be, after you do the parameterization of the surface, you're going to be left with a two-dimensional domain D that you're going to integrate over, and then just like the line integral and the surface integral kind of put together, you're going to put in the R parametrization into the function, or in this case into the vector field. But now you have a vector, so you need to dot this with another vector. And the vector that you're going to dot it with happens to be just like you know how the arc length becomes just the derivative. The surface area without the vector actually is a vector, and so that's what you're going to dot it with. So if you want to just focus on what the differential forms are, and see that if you have an arrow on top, you should be expecting a vector. If you don't have an arrow on top, then you should be expecting a scalar. And the way we're going to differentiate this is that for us, the S will be the surface area, the R will be the arc length. So the book uses little s for the path and line integrals, and they use big S for the surface and the flux. And also they call the path and line integral, they call the surface and the flux a surface integral, although they also use flux integral. Now there's one more thing that I need to tell you about the flux integral and how most of the time it's done. You know, this is one way to do the working definition of the flux integral. Let's call it a working definition. By working definition, I mean this is how we actually compute it. But sometimes you'll see the flux integral expressed a certain way, and the way I'm going to try to do that is to come look at the working definition and then rearrange it a little bit. Actually, I'm going to add in, you know, this whole idea about multiplying by 1 kind of business. I'm going to rewrite this as a double integral of f R of u and v dotted with, now there's this, the ds, we know the ds is the magnitude of the cross product times dA, and so I'm kind of interested in keeping that magnitude of the cross product. Let's save some space here. U cross RV dA. Now, to make these two things equal to each other, the working definition and this other definition, I would want this to simplify to just RU cross RV, so I can think about taking the magnitude, and then you can imagine these things canceling out. Well, the whole reason for doing something like this is, yeah?
So if we're dividing, so if the sake of magnitude is 1, that would just be so just 1 so we get.
Yeah. Yeah. And having a magnitude 1 might become important for us later on. But in any case, this term here is a unit vector that's perpendicular to the surface. And so sometimes we denote this as n. To signify a unit normal. vector? Perpendicular. Normal is perpendicular. So now we can rearrange this back here, and this is sometimes how we see the flux integral written. It'll be f dotted with n. That's this part over here, the f function dotted with a normal vector. And then what's left over? ds without the arrow on it. So sometimes you see the flux integral written with f dotted with n, and that's because if you have some idea of what the normal is going to look like, you can just assign your normal vector, and then you can just do a surface integral instead of a flux integral. Oh, I should have talked about orientation of surfaces first. Oh well. I didn't look at my agenda. All right, are we good with this so far? This is the definition and the working definition of a flux integral. Notice another piece of information that kind of differentiates a path integral and a line integral is that because you're parametrizing your R, your curve C from A to B, it turns out that the orientation is important. And I think we tried to make a point of this earlier. Orientation is important for the line integral. And it's not so important with the path integral because you're taking the magnitude of the derivative. And so instead of looking at the tangent vectors and which way the tangent vectors are going, you're taking the magnitude of those things because the direction is not important. But for line integral it is. So we would kind of come to the same conclusion that for surface integral you're taking the magnitude of the cross product of your tangent vectors, which gives us our surface area, which is why we're integrating over that. But because we're taking the magnitude, it doesn't matter whether our cross product goes up or down from the surface. Well, it turns out that here in your definition of the flux integral, it does matter which direction your normal vector is pointing. And so we have to talk about a surface with a specific orientation. So what's the definition of an orientation of a surface? Let's take a look at that. A surface has an orientation, or it's called orientable, if you can move from one side of the surface to the opposite side of the surface without going over the edge. That seems kind of silly to think about, right? What? A what surface? Closed? No, it doesn't have to be closed. Think about a hemisphere or a bowl. It could be closed, but it doesn't have to be closed. So, like this paraboloid, for example, I'm sitting over here on the outside, and so to get to the inside, I have to hop over that edge, right? If I just look at a regular plane, I can go from one side to the other. The way to get there is to hop over the edge. Yeah. Actually, even if it's a closed surface, there's a definite inside and... Oh, that's weird. Maybe I'll do it. A Mobius strip. Yeah, so when we're talking about orientable surfaces, it's good to talk about non-orientable surfaces. And to tell you the truth, we're really going to be dealing with orientable surfaces, and the non-orientable surfaces are really just special cases. So an example of a non-orientable surface would be a Mobius strip. You guys know how to draw a Mobius strip? Whoa, that was weird. Now, I don't know if I can do it. Oh yeah, that would be just really quick and easy. Just Google Mobius strip and you got it. I guess images would have been good. So there's this Escher picture of the Mobius strip where an ant goes from one side to the other side without having to cross over the edge. And this would make a good tattoo if anybody's looking for a math tattoo. But in general, you have something like this. By the way, why did the chicken cross the Mobius strip? To get to the same side. I think there's some links to topology when you're studying this, because Klein bottles are another type of non-orientable surfaces. So we'll look for that too. So there's an actual Klein bottle that I saw. Oh, here it goes. So this one has no inside or outside. I don't know how to get that water out or that liquid out. Yeah. So anyways, these are like the two classic examples of non-orientable surfaces. Anything else that comes up would be weird looking, I'm sure.
The sphere is orientable because it also has an inside.
It has an inside and an outside. So the sphere, if it's closed, you can't really get through an edge. So in those cases where you have a closed surface, you have a well-defined inside and outside, and that would be orientable. So Mobius strip. There's two dots somewhere. I don't know if it's under the O or the U. I think it's the O, Mobius. And I wouldn't know. How would you pronounce that? I mean, is that German or something? Mobius. That sounds Irish. It's a Mobius strip. Klein sounds pretty German. I don't know. When you study to be a math major and get a PhD, they make you take another language so that you can read some of those. I didn't get a PhD in math, so I didn't take another language. Anyways, you have these two examples of non-orientable surface that we won't look at anyways. But the idea of an orientation is important for us. And so when you're doing a flux integral, when they give you a problem, they're going to say this is your surface and the orientation is going to be this way or that way or depending on whichever way. Okay. So there's two possible answers that you would get. Now, if it turns out that you parameterize a surface with a certain orientation, and you decide to keep that orientation, the difference in the answers, whether you're oriented one way or another, is going to be a negative sign. So you just need to know how you oriented your surface and decide whether your parametrization is, I'll write this down later, but if your parametrization is called an orientation preserving parametrization or orientation reversing parametrization. That's an OPP and ORP. We'll take a look when we look at some examples. All right, so for line integrals, they'll tell you the orientation. For flux integrals, they'll need to tell you the orientation. For the other two integrals, the path integral and the surface integral, orientation is not necessary because your vector that you're dealing with is going to be taking the magnitude, so it's not important. All right, let's do an example. Is it example time? Let me check my agenda to make sure I'm not. Examples, yeah, that's next. Look at that.
Sorry, what were we using for the for?
Pardon me? We need orientation for line integrals and flux integrals.
Outright can't do a flux integral.
Correct. Yeah.
So we say that in a general sense, if it says like clockwise, that could that like be like positive or something? Like if it says counterclockwise.
Well, that might work for a line integral in 2 dimensions, but that won't work for surface integrals because surface integrals in 3D, so the idea of clockwise has to be taken from your view. So if you're looking at a plane, from the top it might be clockwise, from the bottom it's counterclockwise. So you have to be really specific about which way your orientation is going.
Yeah, and then orientable just means you can put a means there's one end on which the normal vector points out of, and one which the normal vector points into. Effectively, so like I feel like
Well, let's do an example, see if it'll clear things up a little bit. We have 5 or 6 over here. Any suggestions? Let's pick one, and I'll pick one from the book, so at least you get a homework done. Which one should we do? Just pick a number, 5 or 6. Yeah. All right, let's do number 5.
surface and flux integrals.
For line integrals and flux integrals.
So a surface integral you could do.
Yeah, except you need to parameterize it, so you probably wouldn't do it. I mean, theoretically you can do it. What am I doing? Oh. Just feel a little flustered this morning. Is it morning? It's not morning anymore. Dang. Close enough. Just gonna go take my kids to school, and there's a flat tire. All right, what are we doing? Evaluate the surface integral. So again, they call it a surface integral, but I'm seeing a bold F and a bold S, so I know those are vectors, so I kind of consider this a flux integral. In fact, let me just cross this out and put flux. Flux integral, vector field oriented surface. In other words, find the flux across this thing. So here's your vector field, x, negative z, and y, and they want the part of the sphere in the first octant. And the orientation, so here they define the orientation for you. The orientation is going towards the origin. Now, let me begin by writing down the working definition of this. with some sort of parameterization. Let's parameterize it using, well, what I think in the past I've called a graph parameterization. And what the graph parameterization is it, instead of u's and v's, I'll use x and y's. And then the z component now is going to be the z component of the surface. So if I take my surface, which is the sphere, and solve for z, and the good news is that this is in the first octant, so x is positive, y is positive, z is positive, everything's positive. And and so when I solve for z and I take the square root, I can just look at the top part. And so the square root of 1 minus x squared minus y squared. Now, my domain, I would try to express this in equations or inequalities, but I'm just going to draw it out and then talk about this a little bit later, because I'm not going to really follow through with this setup, and then we'll see if we can find a shortcut. But if it's in the first octant, I can figure out my z limits, or my z value, my z function. This is the function that's going to be describing the surface. And the shadow that I'm going to have on the xy plane, which is going to be my d, is going to be just a quarter of the circle, unit circle at that. So if I begin to do the work through the working definition that I established earlier, I would need to find RU and RV, and then cross them. So I would actually, instead of U's and V's, I would probably need X and Y. So Rx and Ry. And cross them. But you know what we're going to come up with, don't you? Yeah, I don't know. Something, 1. Or -1. Or +1, -1. That depends on what those other somethings are. Do you guys know what those stars are? Fx and Fy, it's a partial derivative of, well, it's not this function that we're talking about. We're kind of looking at this one, because that's the surface that we're dealing with. So we take the derivative of this. If we call this f, I don't know if that's a good thing to do, but I'm going to call it f. This would be fx and fy. So now here's the thing. Either the fx and fy are negative, or the -1, the 1 is negative. So I either need to have 2 negatives here, or 1 negative here. Now, let's take a look at the description again, and let's see if that can help us decide which way to cross this. The first octant with the orientation towards the origin. Imagine a sphere, 1/8 of a sphere. Imagine a sphere, and imagine putting a normal vector on the sphere. There's 2 ways to make that normal vector. You can make that normal vector going away from the origin, or you can make that normal vector going towards the origin. Wouldn't what make what negative what? What? Yeah. So if your normal You're in the first octant, right? Your normal is facing towards the origin. What can you say about the z component? Z component is negative, right? So in terms of making a choice for your orientation, you want this to be negative, and therefore these other two would be positive. Okay? All right, so again, I'm going to follow through this process just a little bit, and then I'm going to stop at some point and say, oh, maybe there might be another way to approach this. But let's take a look at where we are so far. At this point, we have a parametrization. We have an orientation for our parametrization. And so we have the vector field here. Now, this tells me that our flux integral should be a double integral over this region D. I've defined D up there. And then now I'm going to take my vector field and I'm going to put x in for x, y in for y, and square root of 1 minus x squared minus y squared in for z. And this has a negative in front of the z in the j direction, my vector field does. So I'm going to put negative there, and then my last term is a y, and the y is a y. And I'm going to dot it with this thing that I have. Now, I'm still refusing to compute this, but we'll deal with this later. And then that's my setup. So if I just take the time to compute the fx, fy, then I can perform that dot product. And then there's a good chance, especially this domain, there's a good chance that I'm going to go polar coordinates for this. But I'm going to pause here. And go to this idea that our flux integral can be rewritten as a surface integral if I have some idea of what the normal might be. You could. This is what's happening over here, but I claim easier. Yeah.
Possibly just pick any point on the surface and then just.
Okay. Yes, that's the idea. Pick any point on the surface and point it in. Okay.
Yeah, all we do is get a point on the surface and direction.
Yeah, but we have an infinite number of points on this. What if we randomly pick one, x, y, z? What's my normal?
The magnitude of the cross.
No.
It's exactly what you put it with the arcs.
Kind of. Okay. So far, Matt's got the lead here. You pick a random point and then find a normal. My point that I chose is x, y, z. I know that's not a good point, but that's about as random as you can get, right? Arbitrary. So if I'm on the point x, y, z on this sphere of radius 1, sitting on this first octant, somewhere over here, what's my normal vector? No, there's no dotting going on here.
As long as we're talking about spheres here, the magnitude is going to be 1.
We're talking about the unit sphere. In the unit sphere, the magnitude is 1. Keep going.
And it's going to be pointing out radially from the origin.
Pointing, we want to go towards origin.
No, radially towards the origin.
Radially towards the origin.
From that point.
From that point. My point is x, y, z. All right, my point is 1, 0, 0. What's my normal vector? Not the gradient. You guys keep wanting to go to the gradient. Negative 1, 0, 0, right?
The coordinates minus, or no, it's 0, 0, 0 minus the coordinates. Or just negative the coordinates.
So if I'm on x, y, z, which way is negative x, negative y, z, negative x, negative y, negative z pointing? Towards the origin from that point. Exactly. And it has unit length because we're on a sphere radius 1, so I'm going to point directly towards the origin. And that's exactly what I want. So this is the key, is that if you can find a normal vector that can easily capture this idea, then doing this work is way more process and way more derivatives than you need to do. So that's what makes this form, the flux integral with the normal vector here, that's what makes this form a lot easier to deal with. Does that make sense? Yeah.
So is this just like unique to the sphere, or is it?
Well, it's unique to this particular normal vector is unique to the sphere. If you have a plane, that would be even easier because your normal vector is going to be constant. And if you have some other form that's either a sphere or plane, I guess that's it. That's or maybe a cylinder. If you have a cylinder, that might also have a nice normal for you to deal with. Okay, so there's a handful of surfaces, and usually these are the surfaces that you're going to deal a lot with in physics and engineering, is that spheres and cylinders are going to be really important. And to find these normal vectors for those spheres and cylinders might be nice and easy. If you're talking about a paraboloid, that one's a little bit more tricky. So with a paraboloid, I might want to go this route. Yeah.
I'm not sure what happened there with the. So isn't that negative 1 minus x squared minus y squared supposed to be the z component?
It is for this.
Why is it in the middle?
Oh, that's this because if you look at so this first part, remember, we put the parametrization into the vector field. All right, so let's see if we can continue on with this process, taking advantage of this normal vector. So we're going to actually, before we put in the z, because x is x, y is y, before we put in the z, we're going to perform this dot product. So your s, you're integrating over s again. Your vector field is x comma negative z comma y, and you're going to dot this with negative x comma negative y comma negative z. And then now you've reduced your flux integral into a surface integral. Remember, this s does not have an arrow in it, so it's a surface integral. That's because if you take the dot product of these two vectors, then you're going to just have a scalar. So what is that? I have a negative x squared minus zy, yz. Wait, minus minus is a plus, and then y, xy, x, whatever. Well, that's nice. It's just x squared. Now I have a surface integral where my surface is this parametrization. So I'm going to borrow what I have here, but look at the surface integral now compared to the original flux integral. The original flux integral, had we gone through and started working it out, this would still be correct. We'd still get the right answer. But look at this. Look how much simpler this is. And at this point, there's a negative. At this point, the orientation of the parametrization is no longer important because I took care of that when I put a negative sign in front of my normal vector here. And so now this is just a regular surface integral. So I'll take advantage of this parametrization that I used. So I'll integrate this over the domain D. Again, this is the same D that I'm talking about here. And my x squared is just going to be x squared. And my ds, I didn't work out my ds, but my ds would be the magnitude of this. What's my ds? Should have worked this out. Rx cross Ry, yeah. So again, it's fx plus fy, or fx squared, fy squared. But wouldn't that make that a 2? Because this is x squared over the square root of the stuff, y squared over the square root of the stuff, and this is 1. So you need the common denominator business. Not that big. Evan did this for us last time. We never bothered going through the work. Yeah.
Okay, so f of x would be negative x divided by the square root of negative x squared minus y squared plus 1. Or do I want the same one?
Oh, no, this wasn't what I was thinking about. Anyways, so if we put this all under here, you got x squared over 1 minus x squared minus y squared, because you're going to take it, square it, and then y squared over square, oops, no more square root because you're going to square it, plus 1, and if you have common denominators, right? So the x squared is going to go away, the y squared is going to go away, and you just have 1 over this. Is that right? Well, this wasn't as easy as I thought, but it's still considerably easier than all this big mess over here. Now let's make sure that's right, because we can go on and make a mistake on some algebra here. That would be unfortunate. Does it look right? Just Need some nods from a couple of key people here. Okay. Well, nobody nodded, but we'll move on. So again, my D is a piece of a circle, and I have x squared plus y squared, so it might be natural to go into polar coordinates. So in polar coordinates, we will have, by the way, in polar coordinates, this is going to go from 0 to 1, and theta is going to go from 0 to pi over 2. So when I go to polar coordinates here, my x squared is going to be r cosine theta squared over 1 minus r squared under square root, and then r dr d theta, where my r goes from 0 to 1, and my theta goes from 0 to 2, to pi over 2. What happened to my pen? This should be all purple. Okay, well, this wasn't the easy integral I was looking for, but see if we can have. Yeah, I thought it was going to be easy.
Was it integration by parts?
No, it might be. Oh, you could. It might be trig substitution. So with that, I'm just going to go Wolfram. Should we do this double integral at once? Let's see. Integrate. Let's see. Integrate. We got r squared cosine theta. I'll put th square root divided by square root of 1 minus r squared. Close the square root. I'm just going to put, instead of putting an extra r, I'm going to put r cubed. Okay, matching parentheses, matched up. So the first integral is going to be with respect to r, and r is going to go from 0 to 1. And I'll close that parentheses. And then my next integral is with respect to theta. And then the theta is going to go from 0 to pi over 2. See if it does a double integral for us. Did the double integral, we got the, what's not squared? Cosine needs to be squared. Thank you. Is it going to come out nicer? Is that what you said?
A little bit. I don't know if it's mathematically pleasing.
Pi over 6, that's mathematically pleasing. Indeed. All right, let's, I don't know if I want to check my answer. I suppose we should, since it's checkable. Pi over 6, do they want, let's see, what do they want? I didn't want a decimal, so hope this is right. Negative? We got our thing fixed up. What happened?
I don't think you brought the negative down when we were following.
Oh, I lost the negative over here. Damn. Well, looks like it's right. Whew. So, not that this wouldn't have been wrong, but, you know, like I was saying, the fx and fy are equal to whatever they're equal to, and when you take the dot product here, you might come out with something that might be a little nicer, I don't know. But in either case, you probably want to go to polar coordinates anyways after you set up your integral. So think about that. If you have time, try this. Try going from here based on the information we have, and then, you know, put in this fx and fy that we computed, actually that John computed, and then dot it, and then integrate it, probably go in polar coordinates again. And then hopefully you get the same answer. Okay, wow. So if you have a plane, especially a plane that's parallel to a coordinate plane, then two of your normal vectors would be 0 if you were to find your little n. If you're talking about a cylinder, usually the cylinder is going up the z or the x or the y, then one of your components would be equal to 0 as well, because it would be sticking straight out. So the idea behind, you know, using this form where you can easily or quickly identify the normal vector, the unit normal vector, might be an advantage for simple surfaces like we've been dealing with. And you're going to have a lot of problems that deal a lot with spheres. You're going to have some problems that deal with cylinders. And maybe we might get lucky. You might have some problems that deal with planes. Here's all that other stuff that I already talked about. And here's some examples. And here's a summary of all the integrals that we have, starting from the integral in Calc 2. So I want to put that in the notes today. And we'll take a look at that again and again, a couple more times probably. Because it kind of puts things into perspective. And if we look at the single integral that we've learned in calculus, instead of looking at it as the integral from a to b, we can look at that as an integral that's integrated over an interval, I, where I is your interval. And if you kind of start off with that, then really all the integrals that you're doing will be integrating over some sort of geometric region. A single integral would look at a one-dimensional region. So your one-dimensional region would either be an integral from a to b, or in these cases where you have a curve, that could be in 2 dimensions or 3 dimensions, but it would still be considered a one-dimensional object because it could just be parametrized by one variable t. So here you can think about this as being parametrized by one variable x. But these other two over here you can think about as being parametrized by one variable t, whether you're looking at it in 2 dimensions or 3 dimensions. So those are your one-dimensional integrals. You got a single integral, and the path and line integrals eventually get reduced to a single integral because you're just going to be integrating over one variable. The next is your double integral. And the double integral is integrated over a region D in 2 dimensions. Now, whether this region is on the xy plane or the uv plane or the r theta plane, it doesn't matter. It's just going to be on some 2-dimensional plane. So we use a dA to represent the 2 variables, d something, d something. Now, your surfaces can be seen as a two-dimensional object that's somewhere up in 3D, because the surfaces are infinitely thin, right? So they're just really just a two-dimensional object. Except in 3 dimensions, you get distorted and this weird thing that can happen. But the idea there is that it's still a two-dimensional object that's been parametrized with respect to u or v or x and y that we've been working on, or we've seen parametrizations with r and theta as well. And then this thing gets reduced to something that's happening on a two-dimensional domain. And so you have an R that takes 2 points or a vector, x and y, or u and v, and then gets it sent to some 3-dimensional object. But it's still 2-dimensional. So the double integral, you can think about that as a 2-dimensional object. And aside from just a region on the xy plane, it can also be a surface in 3 dimensions. And then the only other type of integral that we're going to cover is a triple integral that's actually coming from a solid in 3 dimensions. So we have no way of taking that to 4 dimensions or some other weird stuff, so this is as far as we're going to go. All right? Yeah?
As far as flux integrals go, what kind of
Oh, applications? Yeah, I didn't get to the applications. I think that was next in my agenda, so we're out of time. So
There's a lot of applications in electric.
there's a lot of applications, electromagnetism and stuff like that.
We haven't used them.
Yeah, yeah. So
A lot of parts you got there.
a lot of hearts,
Parts.
farts. Oh, FRT. Yeah. Sure is.